now that we've already discussed all about single effect, let's save the best for last, which is the multiple effect evaporators. Now, multiple effect evaporators, I could attest that any chemical engineering students would think twice when solving this problem. I remember nung board exam namin, during review when these certain problems are involved, talagang we will always try to skip this because there are a lot going on in such kind of problems. Pero syempre, depende siya kung ano yung tinatanong. Sometimes kasi yung tinanong lang naman is ano ba yung expected natin na change in temperature. So that would be a very easy one. But when it asks for the steam economy for this the area, knowing that we have a boiling point elevation, then that's really kind of difficult to do. And because I want to show you how evaporator works in a sense na yung posibleng pinakamahirap na lumabas is bibigay ko na yon. Kasi ayoko naman na pagdating sa exam is may mahirap and then hindi ko siya naturo. So, I would rather show you the most difficult problem in the video rather than you seeing it for the first time during your examination. But anyway, I would, of course, try to make your exam a lot easier than this. So, before, when we try to solve evaporation problems, we would always try to neglect boiling point elevation. Sometimes then, nililet natin na yung ating specific capacity of the liquor and the feed being the same or hindi siya nagbabago during the process. But now, let's have a multiple effect wherein wala tayong consider na any restriction. Siguro ang pinaka ina-neglect lang natin nito is yung heat of dilution, which is heat of solution kasi wala naman, and dilution nga kasi wala naman talaga tayong data about that. So, yun na lang yung pinaka-neglect natin. But the rest, lahat is i-consider natin. Okay? And before anything else, before we are able to solve problems like this, especially multiple effect evaporators, let us dissect the problems first so that you would understand how this works. Okay? So, yung simulan natin, a forced circulation. Wala tayong problema doon kasi sabi ko nga any type of evaporator basta same concept lang yan ng material and heat balance. Then the next one would be triple effect evaporator. So I know you've already heard about this triple effect, multiple effect, double effect. When we say triple effect, parang meron tayong tatlong evaporators na magkakasunod siya. So yung feed papasok dun sa unang effect and then lalabas siya dun sa last effect. So it's something like that. So when we say double effect, so meron tayong dalawang evaporators. Now I'll try to draw or represent this triple effect para mas magets natin ng ayos. Okay, so now that I've illustrated this problem, so ganyan yung medyo magiging itsura niya. And pasensya na kayo sa maraming arrowheads. I used to draw PNID lagi, kaya ganito yung kinakalabasan ng mga arrow. Medyo maraming arrows yan. Pero anyway, hindi naman yung concern nyo. So, this is a triple effect evaporator using forward feed. When we say forward feed, meron tayong first effect and then the feed enters at that effect and then it leaves at the last. So, from first going to the second effect and then third and then sa last. Ngayon, meron tayong tinatawag na backward feed. Pag sinabi nating backward feed, instead of starting from the first effect, yung feed natin magsimula siya dito. So, basically, kung meron kayong feed and then third effect, so dito siya ipapasok and then mababaliktad yung ating system. So, para maging ganun siya. Okay? So, maging ganun yung ating system and then lalabas siya dito. Okay? So, that's the backward feed. But the idea is just the same. Doon lang tayo sa last effect ng simula. Pero yung steam naman is mag-start pa rin siya dito sa first effect. Kaya parang nakakaroon ng pagsasalubong yung dalawang yun. So, yun yung parang two types natin na mode of operation. We can do forward feed or we can do backward feed. Okay? So, yun yung sa unang, actually meron pa sa unang sentence and then meron tayong 10% weight sodium chloride. So, pag sinabi natin 10%, yun yung mass fraction ng ating sodium chloride dun sa feed. So, ito na yun, XF equals 0.10. And then, it enters at 37.8 degrees Celsius. So, ito yun, 37.8. So, ito yung temperature ng ating feed. And then, it is concentrated to 50%. So, basically, hindi siya dito, kundi dun sa end ng ating process. So, dun sa L3, kung saan ito na yung liquor 3, meron tayo dyang mass fraction ng ating sodium chloride, which is 50%. And knowing this is sodium chloride, we know naman na meron tayong mga certain assumptions, actually mga conditions to ito na lang gagamitin ko para maganda yung sulat. So, meron tayong mga conditions na ko-consider. One, this is with boiling point rise kasi this one is sodium chloride. So, alam natin na may boiling point rise yan. Pangalawa, CP of the feed is not equal to CP of the liquor. Kasi nga, sabi kasi dito sa problem, kung nabasa nyo na ng buo, the specific heat capacity can be expressed as a function of the mass fraction of salt. In kilojoule per kilogram Kelvin, this is the equation. And as you can see here, yung feed natin, meron siyang certain mass fraction. Yung liquor din dito napapasok. Lalabas. And then, papasok sa second effect, meron din yung mass fraction. Meron din siya dito. So, basically, hindi siya equal. And we also have I think that's all naman muna. Okay. So, yun muna. And then, dun sa ating second sentence, the steam used enters at 58.6 kilopascal gauge and leaves at a slightly lower saturation temperature of 380 Kelvin. Now, this one is very important, itong pangalawang to. Kasi una sa lahat, sinabi dito na ang steam natin is pumapasok sa gauge pressure. So, we know very well na kung ito yung gauge, kailangan natin siyang i-convert muna into absolute pressure para makuha natin yung ating certain temperature dun sa steam na yon. So, to do that, we just add 101.325 kilopascal to make this in terms of absolute pressure. Okay? So, gagawin lang natin yan dyan para maging equivalent na siya dun sa desired natin na pressure. Kasi, kung mapapansin nyo, pag ginamit nyo mismo yan, masyadong maliit makukuha nyo, which is mali yun. Dapat talaga is malaki. Syempre, steam yun so expected nyo na malaki siya. So, ang magiging sagot dyan, if you added the atmospheric pressure, 159.925 kilopascal. And this is the pressure that we'll be using pag nagkaroon tayo ng mga interpolation. And this one is very important, itong lower saturation temperature of 380 Kelvin. So, di ba before we used to have steam, dalawa pa nga example, merong isang hindi nag-condense and then yung isa is nagko-condense. And basically, ang ginagawa lang natin is yung ating steam is nagko-condense sa same temperature. That is because ang mangyayari lang is mag-change lang siya ng phase from steam going to liquid, or kung hindi man siya purong liquid, some of the quality can be more than 50% or something like that. Now, in this case, the steam leaves as saturated pa rin liquid, pero siya ay nagli-leave at 380 Kelvin. So, that's very important because if you would be taking the lower enthalpy for this steam, you might be using the initial condition. Kasi nga, usually, ganun ginagawa natin. But, in this case, specified yung ating condition na saturate at 380. Actually, it should be 380. So, kaya ayun, yun yung ating gagamitin na condition. Okay? So, we're done with the second sentence. And then the third one, the absolute pressure in the vapor space of the third effect is 6.76 kilopascal. So, this is PV sub 3. That's 6.76 kilopascal. Absolute naman yan. So, di natin kailangan convert. This vapor space, each one of them has its own vapor space. Ito yung sa effect 1. Ito yung sa effect 2, and then ito yung sa effect 3. So, dun sa vapor space ng effect 3, ito yung ating pressure, or dun na yung ating operating pressure mismo na sinasabi. Okay? And then, sabi dito, the feed is 13.608 kilograms per hour. So, ito na yung feed. And then, the heat transfer coefficient. So, ito na yon yung mga heat transfer coefficient. So, siguro ilagay na lang natin dito sa baba yung mga values ng ating heat transfer coefficients. So, we have U sub 1, that's equal to 6246. And by the way, the unit dito is in watts per meter squared Kelvin. Okay. So, mahalaga itong U1, U2, U3 na malaman nyo kung saan siya ilalagay. Kasi, what if it's backward feed? So, basically, mababaliktad yung ating mga overall heat transfer coefficient. Pero, syempre, depende yun sa designation ng problem. Kasi, what if backward feed siya, pero sinabi pa rin na dun sa arrangement, ang U sub 1 niya pa rin is yung ginamit is dun sa naunang effect, sa last effect. So, may iba pa rin siya. Pero for feed forward, laging ganito yung arrangement lang natin. Yung U sub 1 is yung first effect, then U sub 2, second, and then third yung U sub 3. Okay. So, yun na yung ating mga given, and then we start solving this. And the first question is calculate the surface area. Okay. So, sabi ko nga kanina, this is one of the most difficult and tedious. Actually, di naman sobrang hirap, pero ang trabaho niyang gawin kasi nga, una sa lahat, there are no straight or direct ways na para masagutan natin to kagaya ng ating mga sinosolve na pwedeng gamitin natin na shift solve, ganito, ganyan. Kasi nga, wala tayong general equation na pwede natin gamitin para dito. So, ang gagamitin natin is lahat, same process pa rin, enthalpy balance, heat balance, material balance, but alam naman natin na related sila sa isa't isa. Yun yung nagpapahirap dito eh. Yung degrees of freedom niya medyo dumadami as well as the number of equations. Kaya, as much as possible, i-decrease natin yung mga yon dun sa conditions na in-specify sa atin. And the other condition na binigay sa atin dito is that yung ating specific heat capacity is dependent sa mass fraction. So, ilagay natin dito yon. Okay? So, bakit ko ba hina-highlight itong specific heat capacity na to? So, sobrang importante niya kasi gawa ng yung ating kasing specific heat capacity, di ba? Usually, they are dependent on our temperature. But in this case, kung given na tayo ng mass fraction, it will be a lot easier for us to find the value of CP instead of using temperature. Kasi pag temperature yan, double assumptions gagawin natin. I-assume natin na nandito yung temperature and then kunin natin yung CP. Pero if it's mass fraction, I mean, mag-assume pa rin tayo pero it's not really that complicated compared with temperature. So to start with, let's find the other properties that we can obtain from the given. In general, kailangan natin, kapag ka meron tayong pressure, hanapin din natin yung temperature doon at saka yung enthalpy na mabubuo ng water doon sa pressure na yon. Kasi, basically, di ba, kung meron tayong vapor space, doon lagi nag-evaporate yung ating water. So, basically, ito yung vapor space pressure natin, meron din yung temperature kung saan supposedly dapat nag-evaporate na yung ating tubig. But, we do have boiling point. So, this will be very helpful para ma-check natin kung ano ba yung boiling point rise kasi we're also given with this fraction. So, basically, magi-start ako ngayon sa siguro sa third effect. Hindi. Start muna tayo sa first effect kung ano yung pwede natin itong makuha. Basically, ang pwede natin itong makuha is enthalpy and then proceed ako sa third effect. Kasi itong second effect kasi nasa pagitan nila so wala tayong makukuha or ma-generate na data from that. Even dun sa problem natin, walang specify na any given value for our second effect. Okay. So, we start with effect 1. So, this is, lagay natin is effect 1. Okay. So, yung ating steam, we know naman na yung steam natin is pumapasok siya at this absolute pressure 159.925. So, you can find a value for the temperature at that point. Pag nag-look kayo sa peri dito, yun lang naman, 159. Oops. Saan na pala tayo? So, chapter 2. And, syempre, pag hindi sinabi sa problem kung siya ba ay superheated, i-assume nyo lagi na siya ay saturated. So, you go to this, yan, punta lang kayo dito sa ating Paris handbook, and then thermodynamic properties, and actually, hinighlightan ko na ata siya. Ayun, ito na yun. So, ito yung saturated property niya. So, at 380, 390, dun sa pagitan na yan. Kasi, ayun, ang ating pressure is 159.925 kilopascal. So, in megapascal, that's 0.159. So, dito lang kayo mag-interpolate in between those values. Okay? So, pag nagawa nyo yun, na makukuha nyo sagot is 386.1183 Kelvin. Okay, so ito is na pre-compute ko na yung mga values dito kaya magtataka kayo ba't ang bilis ko mag-interpolate. Okay, so kasi pagka ngayon lang din ako mag-interpolate, matatagalan tayo masyado dito. Okay, so yun yung ating inlet ng steam. Pero yung ating outlet, so we have to specify that. So ito yung ating outlet, siya is 380 Kelvin. Ito yung ating outlet. So mapapansin nyo, diba, dito sa ating condition, mas mababa yung ating outlet. Yun yung sinabi dito sa problem na medyo mas mababa yung saturation temperature niya. Okay? So, but with that, na-condense pa rin naman yung ating steam. Hindi nga lang siya sa same temperature. Pero, we won't be accounting na yung ating sensible heat kasi medyo negligible na yan, knowing na sobrang, ano naman siya, sobrang liit naman ng kanyang difference doon. Okay, so again, meron tayong steam, so we need to find the enthalpy for steam. So we enthalpy of steam. Okay. So our enthalpy, so balik lang kayo sa thermodynamic properties, check nyo tong inlet na to, 386. So makakuha kayo ng enthalpy that is 2697.7455. That's in kilojoule per kilogram. Pwede rin ang unit nyo is joule per gram. Okay. And then how about this 380 Kelvin? Gagawin nyo lang dyan since meron kayong H sub S na condensed. So you go back to the Paris handbook and then check on 380. So kung ano yung saturated property niya na liquid, ito lang yan. Hindi, internal energy. Ito, kukunin nyo lang yan and then just convert it to the desired unit. So with that, you will be able to get 448.4722 kilojoule. Kilojoule. Yan. Okay. So, syempre, kailangan natin ng ating lambda S. So, ang ating lambda S or yung ating tatawag na latent heat of condensation, our latent heat of condensation is equal to 2249.2733. That's kilo, same unit lang, no? So, ito naman is nakuha lang dun sa difference ng dalawang yon. To be exact, pwede kasing ang gawin natin dyan is itong HS kasi, hindi lang siya technically subtraction, no? Basically, kung ang gagamitin mo naman is yung ating previous way kung saan in-evaluate mo siya in terms of the same pressure and temperature, same condition lang dun sa inlet, pwede kayong gumamit ng sensible heat in the sense na mag-start ka dun and then ibababa mo pa yung iyong value to a point that's 380 Kelvin. So, from 386 minus 380, then that's around 6.1183 Kelvin delta T. So, multiply mo siya sa specific capacity ng vapor or ng steam. So, yun yung magiging value mo ng lambda S. And basically, actually, ito na yun eh. So, gawin natin siyang ganyan, HS minus small hs, para ma-specify natin na hindi talaga siya nag-condense lang. By virtue na meron tayong dalawang state changes, di ba? You can just subtract those two and then makukuha mo na yun according to, yun nga, state functions natin, di ba? So, tapos tayo sa steam, that's on the effect 1. Let's try moving to effect 3. So, dito ko siya lalagay, effect 3, yung mga pwede natin na makuha based on the given. So, we know very well na yung ating pressure right here is 6.76 kilopascal. Absolute yan. So, from that, we can just solve for the vapor space temperature at the third effect. So, doing that, you will be able to get 311.22 and then 60 Kelvin. So, yun yung ating temperature dito sa ating vapor space. And to be able to obtain our enthalpy from that condition, enthalpy at, let's say, at vapor 3. Okay? So, we know very well na kailangan natin ito is yung vapor space na enthalpy. So, vapor enthalpy, vapor space. So, that's HV then 3. Okay? So, ito yung kailangan natin dyan na property, diba? Pero alam naman natin na this has a boiling point elevation or boiling point rise. So, before we could able to find HV of 3 muna na final, we could just find the boiling point muna nito, boiling point rise nito. Kasi, given na meron tayong TV3 which is 311.2260 Kelvin, we can convert this in terms of Fahrenheit and we'll be able to obtain 100.546.7. So, that's in degrees Fahrenheit. So, gagamitin muna natin to before we are able to find the final enthalpy at the vapor at effect 3. So, to do this, again, i-apply natin yung concept na napag-aralan natin before. We go back to chapter 11. And then, evaporators. then we check on the table. Okay. Okay. So from here, makikita nyo is yung ating chart. And remember, ang wala sa atin is yung ating final liquor temperature dito sa 3 na to. Ang meron tayo is vapor chest. That's 100.5467. So, what you have to do here is hindi siya mag-start kayo sa 100, kundi mag-a-assume tayo kung ano ba yung ating maging sagot. So, we start with 100 and assuming na meron siyang boiling point elevation. And yun nga, so since meron siya, let's try doing 120 muna kasi yun na yung parang lowest dito. So, let's try 120. So, we started 120. So, BPR natin assume is 20. So, we project this to sodium chloride. Okay? And then we go back to the concentration dun sa liquor natin. And the concentration sa liquor is 50%. So, that's 0.5. So, you go back to 0.5. Okay? So, this is this one. So, kung mapansin nyo, yung ating answer is around 40. Okay? So, with that, let's increase our assumption kasi mali yung ating assumption eh. So, let's do 40. Let's try 140 in this case. So, we have 140. Okay? So, move natin to para mag-connect pa rin siya sa sodium chloride and then we project back to our 50%. So, with this, we have 50%. Okay? So, yun. So, it's around 40. Kasi ito is 45 yung gitna. So, around 43 yung ating magiging sagot dyan if ever. And then, let's try increasing kasi, diba, this is assumed 40. So, we move this further sa 43. So, basically, dito lang yan, mamumove. Okay? And basically, kung makapansin, hindi na siya nag-move talaga ng sobra dito, no? You can just move this a little and then move lang natin to ng konti, no? Pero mapapansin, hindi na siya masyado nag-deviate dun sa ating 50. So, yan. So, you could just say na this one is around 43 or 44. So, I'll just use 43 na lang kasi yun yung parang nauna natin na in-assume. Okay? So, with this, yung ating BPR dito sa ating effect 3, alam naman natin na dito is ano na siya, 43 degrees Fahrenheit. So, knowing na yun ay 43 in terms of degrees Fahrenheit, to convert that into Kelvin, we divide it with 1 by 1.8. So, the answer would be this one in terms of Kelvin. So, hindi ko na siya bibigyan ng value. So, hayaan natin na ganyan siya. So, with that, we can now determine our TL sub 3. Kasi, di ba, kung meron tayong BPR, we know very well na yung ating TL sub 3, which is ito yung liquor temperature, is syempre, ito yung vapor chest temperature plus the BPR. So, if we add those two, parang ano lang yan, TV sub 3. So, parang TV sub 3. And then, plus BPR. Actually, kaya ako hindi nagsusulat dun sa pen kasi I want to have a very good handwriting dito kasi pagka pangit ang sulat ko, medyo mapupuno agad yung ating solution dito. Anyway, so, yun nga, TL sub 3. So, we can now find it and the value for that will be is 335.1148 Kelvin. So, yun. Nagdagan na yung ating mga given dito. Meron na tayong TV3, meron na tayong TL3. So, meron na rin tayong BPR and ito is nakuha natin based dun sa ating mga given dito. Now, we can just look for the value of HV sub 3 dito. No? So, again, para makuha itong enthalpy ng vapor with boiling point elevation, you start with the vapor enthalpy of the condition where it started. So, parang dun sa vapor space niya, which is 311. So, you obtain the value of that HV, and then the HV that you'll be obtaining from that is 2572.24184. So, pwede nating sabihin na itong value na to is yung kanyang enthalpy at saturation temperature sa vapor space. So, yun. And then, i-add natin ngayon kasi diba nagkaroon na tayo ng boiling point rise. So, technically, naging medyo nag-above siya dun sa kanyang saturation. Medyo naging superheated yung ating vapor. So, yung kanyang outlet magiging merong counting sensible heat, so that's 1.884. Yun nga pala sa English, sa ano ba yun? Sa SI, yung 0.46 natin before maging 1.884. So, ito yung parang specific heat capacity ng ating vapor. So, multiply this with the boiling point rise, which is 43 over 1.8. Okay? So, yun na yung ating HV sub 3. So, HV sub 3 is equal to 2617.2485. And the unit is kilojoule per kilogram. Okay? So, lagyan natin ng note dito sa taas. Ito. Ibahin natin yung kulay. So, ito is specific heat capacity of this one is specific heat capacity of vapor. Okay? In SI. Okay? So, kung meron pa tayong mahanap dito is siguro yung ating heat of condensation dun sa saturation temperature natin. Diba? Pwede natin siyang makuha. Kasi knowing na nagko-condense din naman ito on the outside, pero hindi naman talaga siya required kuhanin. Pero for the sake lang ng problem na to, para maging consistent tayo sa lahat, kasi kukuha natin yung lahat kunin na lang din natin sa kanya. Kasi if ever nadugtungan natin to, diba? Gagamitin din natin yan. So anyway, yung ating lambda S, so ito yung ito yung ito talaga yung change na sinasabi natin kasi constant temperature ating ko-consider dito. So, lambda V3 siya kasi hindi naman siya S. Okay, kasi siya ay nasa vapor. Vapor space, diba? So, this is equal to yung ating HS, which is ito lang yun, yung saturation, minus yung ating HV na nandun sa ating liquid phase. Actually, di ko siya dito sinulat. So, kung babalik tayo dun sa ating thermodynamic properties, di ba alam naman natin na meron tayong dalawang saturated properties, then meron tayong liquid, and then meron tayong gas phase. So, yun. Kunin nyo yun sa liquid phase, and then subtract nyo from this so that you'll be able to get this latent heat of vaporization dito sa vapor space 3. Pero sabi ko nga is hindi naman natin to talaga kailangan, kaya siguro hindi ko na rin nasulat. Okay? So, para maging consistent tayo kasi kukuha natin lahat later. Okay, so okay na, kompleto na natin lahat yung ating mga given from this is actually our given from the problem, and then ito yung ating mga properties na nakuha based sa given natin. So, medyo marami naman tayo nakuha, And then, to start the problem solving dito, mag-a-assume na agad tayo. Okay? So, gawin natin is trial 1. Lagyan natin trial 1. Okay?